Hi, I am Zubair. This video series documents my journey through a wonderful book written by Sir Roger Penrose. The book is titled The Road to Reality, a complete guide to the laws of the universe. For a long time, I was looking for a book that would help me in understanding ideas behind different mathematical concepts. This is very important in order to understand how to think about mathematics and how to apply it. This book was suggested to me on various online forums. I have decided to document and share my journey through this book. It is primarily a self learning exercise. I'll try to follow the book closely and link its contents with what I have learned in the past. My understanding of these matters is highly flawed, and I would like if the viewers were to correct me. I do hope that these excerpts will come in handy to others like me uh, through their journey uh, to understanding mathematics. Moreover, this is my first attempt at recording, so please forgive my shortcomings in that regard. Let us start with some of the things that Roger Penrose discusses in the preface of the book. This book was written at the close of the 20th century. It was first published, I think, in 2004. It's a very hefty book, around about 1100 pages. This book basically provides the overview of our current understanding of the physical universe. Moreover, it also contains Mr. Penrose's views about possible directions in the future and his comments about our current understanding. This book details an overview of the mathematical ideas that form the basis of our physical understanding, and then it links them to the current physical theories, theories of space time, the quantum mechanics, etc. etc. Moreover, it also provides a possible framework or how to for the scientific community on how to proceed into the future. Some of the questions that form the backbone of the things that are discussed in this book include: what is mathematics? So, the idea, what is mathematics and what is its relevance to the physical world? This is a very debated concept. What are mathematical entities? For example, if we have a set such as or if we have a number, any real number such as 2, or if we have, for example, other mathematical entities such as matrices, what do these entities have an existence, and how do these entities exist in relation to our physical universe? And then there is a question that mathematics is a sort of a logical language. It has its Mathematics has a set of objects, and there are relationships between these objects. Mathematics is basically a study of these two things: what these objects are, what are the relationship between these objects, how these objects change under different interactions, and how these different structures are related to one another. In one important question is, why does the physical universe that we know of, why does it follow the laws of mathematics? Our experience teaches us that physical laws are best expressed in the language of mathematics. But why is this so? This is a very important mystery. This is a very intriguing mystery, which is yet unanswered, and Mr. Penrose tries to look through this mystery to find an answer. In the preface, he mentions a story about how he once met an acquaintance of his mother's who, even though was related to an eminent scientist, but could not understand the concept of fractions. Most importantly, why is it that the fraction such as 3 over 8 is the same as the fraction 6 over 16? That is the art of cancellation. How we can cancel the numerator and the denominator, the common terms in the numerator and denominator, and get the equivalence relation between these two fractions. Here he tries to look at the ideas behind fraction to explain that the cancellation which comes so naturally to the students of mathematics is a very deep concept. It's not as simple as it seems. So basically 3 over 8, or this fraction, is a mathematical entity, and it can, in the physical realm, this can be expressed as basically this circle, or we can say a pie or a cake, which has been divided into 8 equal parts, and we take 3 out of these 8 equal parts, and this is a fraction 3 over 8. Or that we have 8 balls, out of which we pick 3 balls, so this is also 3 over 8. Or we have a rope or any stick which we divide into 8 equal parts, and then we take 3 parts. So these are all physical representations of the fraction 3 over 8. But what is very important, he mentions in this book, is that the mathematical entity 3 over 8 is a very precise concept, while all of these physical objects basically are imprecise depictions. These are physical situations to which this precise concept is applied. Another important thing that we can see over here is that even though all the 3 situations depict the same fraction 3 over 8, but these situations have very little in common. The mathematical entity, so we can note, is a very precise concept, and it is basically an abstraction of the reality. It's not the reality in itself, this number. Another thing that is hidden behind this number 3 over 8 is the assumption. We assume basically that all the pieces that we have made in this physical world, all the pieces are the same. So each piece of this cake, this one and this one, or all the pieces are the same, or all of these balls are basically same, indistinguishable, or all these pieces basically are of the same length. So this is basically what we usually mean by fractions. But the question is, why is it that the fraction 3 over 8 basically is equal to the fraction 6 over 16, and this is equal to the fraction 9 over 24, and so on? Why does this hold? We have seen in previous mathematics that this is because that the numerator and denominator of the fraction 3 over 8, when multiplied by the same whole number, yields an equivalent fraction. So 3 over 8 is 3 into 1 over 8 into 1. 6 over 16 is 3 multiplied by 2 over 8 multiplied by 2, and similarly 9 over 24 is 3 multiplied by 3 and 8 multiplied by 3. We can write this in a general form: 3 multiplied by n over 8 multiplied by n. Where n is an whole number. Then we can see that since it is 3 multiplied by 1, by usual rules of division, we can cancel out this one from the top and this one from the bottom, this 2 from the top, this 2 from the bottom, and this n basically from the top and from the bottom they divide. So we have 3 over 8. So all of these fractions, 3 over 8, 6 over 16, 9 over 24, are basically equivalent. But why is this so? How can this be defined in terms of mathematics? So then Mr. Penrose discusses that in mathematics, what is the fraction? How is the fraction 3 over 8 actually defined? So he mentions that 3 over 8, the best, most like an imprecise definition of 3 over 8 that would match the precise mathematical definition is that 3 over 8 is something with 3 on the top and 8 on the bottom, which if we attempt to write it more precisely in mathematical terms is that 3 over 8 is represented by an ordered pair of numbers 3 and 8. What does an ordered pair mean? An ordered pair basically means that the pair 3 8 is not the same as 8 3. If 3 8 were the same as 8 3, this would basically be an unordered pair of numbers. But even this definition has its problems, because then the fraction 6 over 16, which we know from the rules of cancellation, is equal to 3 over 8. 6 over 16 is an ordered pair 6 comma 16, which is not equal to the ordered pair of 3 and 8. So how do we incorporate cancellation into the definition? This, as Mr. Rogers explains, is done by building cancellation right into the definition of the fraction. So we define that the ordered pair a multiplied by n comma b multiplied by n is the same fraction as the ordered pair a b, where n is a non-zero whole number. Moreover, as in fractions we know, b is not allowed to be 0. So this can be written more mathematically in this form over here, that a over b basically equals a over b, where both a and b are multiplied by a non-zero whole number. But this definition does not tell us what a fraction really is. All this tells us is that how a fraction is represented, how it is written, how it is written. So how do we actually define a fraction? This as is explained is done in terms of the notion of an equivalence class. The notion of an equivalence class is very important, as is mentioned in the preface, because it will be used throughout the book to define more difficult and more advanced concepts of mathematics. So what happens is that 3 over 8, the fraction 3 over 8, is defined as the infinite collection of ordered pairs, which is 3 comma 8 minus 3 comma minus 8 6 16 minus 6 16 9 24 minus 9 minus 24. So we can see that the things that are in this infinite collection basically are all the ordered pairs of the form where n is an integer. That is, it can either have positive or negative values. So this infinite collection is basically this fraction 3 over 8. We can see that the notion of an equivalence class is it's a class of entities which are basically defined to be equal or known to be equal. Once we have defined what a fraction is, then we can define the laws of addition, subtraction, multiplication and division for such equivalence classes. Moreover, It We can also define whole numbers as a special case of fractions, where we can define them as any ordered pair of the form where a is a whole number. So basically, if we want to define the whole number 3, we can define it as a fraction 3 over 1, which is basically the collection of the ordered pairs 3 multiplied by, as we have seen above, where n is a non-negative integer. Now we can see that defining 3 over 8 as an infinite collection gives us mathematical consistency. So the notion of equivalence class gave us mathematical consistency because it helped us to build the notion of cancellation right into the definition of a fraction. But this does not give us intuitive understanding. So the cost of mathematical consistency in this case was intuitive understanding. How can we look at the physical representation that we had seen earlier of the fraction, basically 3 over 8 how can we see this from its definition as an equivalence class, which is an infinite collection of ordered pairs? This is not possible. It's very difficult to imagine such a physical application from the notion of equivalence class. So it is better to think of 3 over 8 as an object which, when added to itself 8 times, gives us 3. We can see that to give some understanding to the concept of cancellation, why it works, we had to define the fraction 3 over 8 as an equivalence class, such that this is equal to all the ordered pairs where n is an integer. This definition has given us mathematical consistency. Now we exactly know why cancellation works and why it is supposed to work. But this particular definition has come at a cost of intuitive understanding. But now this is it's very important to understand that if we do not understand certain mathematical concepts, this is because we have not taken a deep look at what is behind these ideas. So we must make a conscious effort, to understand the background of mathematical ideas, why these things work, how these things are defined in mathematical context with rigor, but to also balance this with an understanding and knowledge of how these things occur in the physical world. At the end of this section, I would just like to point out that to learn mathematics, all we need is the will to understand and think about various ideas. We must be very open-minded. When thinking, open-minded and patient, I would add, when thinking about different mathematical ideas. And we must practice a lot of problems, not only about how calculations are done, but how different ideas are constructed and applied. Moreover, when people usually say that they do not know mathematics or they cannot understand mathematics, most of the times they are confused about arithmetics, because this is what they generally encounter in daily life, in addition, in subtraction, in multiplication and division. And if they cannot do it quickly, like some people are very gifted at this stuff, they think that they cannot do mathematics. Whereas mathematics is not about calculation, it is more about the relationship between structures, and different relationships between structures, and how different structures are equal or different from one another. The only thing I would like to say is, do not give up. Do not give up anything. You can learn anything by practice and by hard work. But it is also very important to find good sources, such as this book or other books that you may find helpful to guide you through the learning process. We hope to meet again soon with discussions on later chapters of the book.